Hi, everyone. My name is Dale Kim, and I'm the Senior Director of Technical Solutions at Hazelcast. And welcome to my presentation, Fast Access and Fast Action Drive Real-Time Analytics. And so you might know that CXL helps out quite a bit in terms of performance among computer systems. And I want to talk about that from the context of a software platform, more specifically, a real-time data platform in which you can handle real-time responsiveness through your business applications. And so what I want to talk about in this session is first, how we view real time. And so how it's expanded beyond the scientific definition and how that's become valuable for a lot of ways that people think about how to handle business and how to handle their operations in a real-time manner. Then I want to talk about Compute Express Link from a software perspective and talk about a lot of the issues and the examples of how real-time is inhibited by some of the challenges today, especially the bottlenecks when it comes to different types of operations that we're very accustomed to. And finally, I want to talk about some software deployment examples to give you an idea of how a software-based data platform would take advantage of CXL. And so if we think about the traditional definition of real time, or maybe even the scientific definition of real time, often it has to do with meeting a commitment for a given time requirement. And so oftentimes that means very low latency. And if you look at the examples here, whether it's driving a car or airbag deployment, air traffic control, or even controlling robotics, all of those things require almost instantaneous action to some event. And so if you're driving a car, you want to make sure that it responds to anything in the road or any changes that it needs to respond to right away. There's no good if it happens a few seconds after it recognizes the event. So a lot of these times that guarantee is responding within a few milliseconds. And in any of these examples, that's the case. And what's interesting in business today is that real time is definitely expanding in terms of what value we get out of it. And it doesn't necessarily have to be in milliseconds, but it's basically more about being on time. And so a lot of times people talk about real time acting instantaneously. And you'll hear a lot of people say that nothing really is instantaneous when it comes to computer systems because there's always some latency associated with moving electrons. And I think that's one reason why people take a more broader view of what real time means, especially in a largely batch driven world for a lot of computer systems, especially dealing with large data sets, where you do want to create more efficiencies by collecting all the data together first and then running computer systems that'll process this data all together. And so that tended to be a very efficient way to crunch through large data sets, but there are also ways in which you can respond to data right away. So if the data represents some type of event, you can take action and give your business a competitive advantage. So this notion of responding on time might be within milliseconds, but oftentimes if a human is involved in getting some alert or being involved in taking that action, then just being able to respond within a reasonable time frame becomes the definition of real time. And ultimately, the way I see real time is just avoiding a lot of these built-in delays that are trying to overcome some bottleneck that's created as a result of the workloads that are being placed on the systems. So whether you're waiting for disk writes, if you have a lot of operations going on, if you have data in motion from, say, IoT devices coming in at a fast rate, how do you handle that? And a lot of times the bottleneck is writing to disk in a specific format. And so one way to resolve that in terms of processing fast moving data is to wait for the end of the day and then process it all together. And of course, you have that huge latency of waiting till the end of the day. And so what are some options in trying to address that? And I'll talk a little bit more about that. And of course, I would argue that anytime a system requires human intervention, then you necessarily are not running a real-time system. So the system on the computer's behalf might be pretty quick, but if you have to rely on a human to make a decision, then you're necessarily at a disadvantage there. And so I do want to state, though, that real-time capabilities start with low latency. So if you have a system that removes all those bottlenecks so that the system can respond instantaneously, then you do have a head start in being able to deliver that real-time responsiveness that everybody's looking for today. So let's look at a simple diagram of a distributed software system. And whenever you have a distributed system where each of the nodes are working together to form a bigger solution and to solve a big problem, there's a lot of coordination, and that coordination comes in the form of network calls between each node. And depending on how simple or how complex your distributed system is, you could end up with a lot of traffic. And of course, you want to make sure that that traffic doesn't become the bottleneck, but of course, it oftentimes is. And so if you look at some of these distributed systems, there are different levels of interaction where on one end, you might have a simple NoSQL database in which a lot of the operations are simply about reading one record at a time. So if you only need to read one record, then certainly the coordination of actions between each of the nodes isn't as severe and isn't as critical, and therefore the responsiveness can still be pretty good. But now a lot of these NoSQL databases have SQL running within them. So now you can run SQL queries that take a look at that data and joins them together and puts them in some long, oftentimes long, cohesive list of results. And that does require a lot of traffic between all the nodes. And so again, if you have to depend on that, that represents a bottleneck for delivering fast results. And then there are other systems where things like in-memory data grids, where processing is done on each of these nodes. So rather than the more storage-focused model of databases, an in-memory data grid is about submitting code to the entire cluster so that work is being done on each of these nodes on its local data, and then collating all that information into one end result. And a lot of coordination is involved there as well. So you want to make sure that the interconnects between each of these nodes are as fast as possible to enable that overall fast responsiveness. So let me talk about a conventional analytics architecture, mostly from a software standpoint. You oftentimes start with, well, you always start with a data source, like an online transaction processing database. So that's the thing that collects or creates the data. Now, we all know that when you want to do analytics on that data, you often have to send it off to some other analytics database, like a data warehouse or a data mart. And so in the middle of this pipeline, you have these extract, transform, load tools, or ETL tools, to modify that data into a format that's more conducive for analytics. And then you write it into some other store that's optimized for analytics. So again, that could be a data warehouse, it could be a data mart, any technology that's separate from the transactional databases so that you can have end users running queries. And so when you have end users talking to that optimized store, you oftentimes want fast access and you want the tools to be able to run analytics, i.e. run different queries at fast speed. And so of course, you face a lot of bottlenecks in part of this pipeline. The first bottleneck is in the extract, transform, and load part, where you necessarily have a batch-oriented process to run the extraction, the transformation, and the loading, and so that adds some latency. And then certainly writing that information into the optimized store, which is often disk-based, will add some latency. And of course, the end user, as I mentioned before, represents that final bottleneck in responding in real time. So you have a couple of points here that represent slowdowns in a pipeline that you otherwise want to run as quickly as possible. Let's look at a more modern view of real-time analytics, which incorporates newer technologies like message buses, especially things like Kafka and Pulsar. Now you'll notice that in the middle, instead of simply extract, transform, and load tools, we have something that's referred to as streaming ETL. So that's good for taking information from some of those message buses like Kafka and Pulsar and processing them as the data is created and then putting them into that optimized data store. So this is an improvement over the traditional analytics architecture in that it can take data in motion, prepare it for analytics, and then write it to the store. Yet we still see a lot of the same types of bottlenecks. And so while streaming ETL tools are intended to handle data in motion and therefore act more instantaneously on that data, that still represents some processing bottlenecks as a result of those intermediary steps that you have to take prior going to the next step. And that next step, of course, is writing it into that database, which we had mentioned earlier. It was a bottleneck. And of course, the bottleneck with the end users at the very end. Another model of real-time analytics is similar to the previous one, except that in that middle part, you can write data into something like a data lake. And a data lake is a distributed system that's very good for ingesting data right away. And oftentimes you're putting in raw data without a lot of transformations. But once you have it within the data lake, then you can make the transformations that make the data more suitable for analytics. And then from there, you can write it over to an optimized data store, and then you can have end users query it. Now, some people would argue that the data lake helps with the overall process, but the fact is there's still a lot of work to be done in the data lake. And so there's still a bit of a bottleneck there. But the point is that no matter what you have in the middle or at the end, you still have these remaining bottlenecks as part of your overall real-time analytics architecture. And so what I want to talk about is how things can change when you make some adjustments to not only your hardware that on each individual server, but also tying that in with CXL interconnects among your different nodes. So here's an architecture for a real-time server as you would expect it in using conventional technologies. So you have RAM, and for the purposes of simplicity, I've excluded things like disk and CPU from this diagram. But you have RAM that you can expand in various levels. You have the operating system, and you might have a memory manager of some sort. In many Java applications, that's the JVM heap. And so that's the thing that manages the memory for your use by your applications or by your software data platforms. And so you typically, at that second highest level, have some framework in which you can build your applications, whether that is a data platform or a database. And at the top, you have your business applications that run the business logic that you need for your operations. And then you have a series of these hardware nodes that are connected together. So of course, if a lot of the work needs to be coordinated with other nodes, so you want to make sure that the traffic runs as quickly as possible when sending data across all the other nodes. Now, what if we look at a different architecture where instead of relying on RAM, which a lot of people have assumed would be cost prohibitive for their environment, you looked at alternative memory technologies like Intel Optane. And the advantage of Optane is that you get more dense memory configurations on single servers for approximately half the cost of RAM. And so now these in-memory speeds that you desire are much more cost effective. And so you can build out these extremely fast servers, network them together, and build essentially a supercomputer that coordinates all their efforts as if it was a single computer, and certainly simplifies the deployment of your applications in such an environment. And here's where a memory manager like MemVerge becomes particularly useful, because MemVerge acts as an abstraction layer to technologies like Intel Optane, so that any of your existing applications don't have to write to the specific API that that the Optane modules require. MemVerge abstracts all that away. So any application or any platform that you run on your nodes will go through MemVerge, and you'll get the advantage of non-volatile memory in conjunction with volatile memory speeds. And so that's what Intel Optane is about having persistent memory, but also it could be used as an alternative to volatile memory like RAM. And then you have technologies like Hazelcast that will run on top of MemVerge. So you get that high performance from the Intel memory modules and get much more memory density within your hardware. And now you have greater allocations of data in which you can do processing and provide analytics. And so what I want to talk about here in terms of real-time analytics is that there's this potential for a shift of being very storage focused. So moving from a database-centric world to something that's more focused on the processing. So data places still play a big role in storing your large volumes of data, but what if you had a processing platform that could incorporate more of that data in memory, process it in memory, so at very high speeds, and then deliver that for real-time analytics? And that's where we see a lot of things going, and especially with improvements in speed in all computer systems, you can realize these high performance systems at a much more cost effective level. And so just to quickly talk about the Hazelcast platform, you see us in the middle, and essentially we're an engine that has stream and batch processing tied in with in-memory data storage. And combining those two capabilities allows you to do a lot of analytics, a lot of data processing at very high speeds. And because we're a distributed system, the faster that you have interconnects between each of the nodes that we're running on, the faster the overall throughput will be and the lower the latency. And here's a model for real-time analytics that is extremely powerful when using something like the Hazelcast platform with MemVerge memory machine and with Intel Optane. And so what you have here is data on the left that's created from a variety of sources, and it could be stored in something like Kafka or Pulsar or Kinesis. And we'll read that data. And there are a number of things that we can do as we read it in. One is that we can ingest the data and aggregate it. In other words, put it in a format that's suitable for analytics and index it, and then dump it into our own memory store and get that high-speed data mart that end users can query on. Another thing we can do is just pass that through into the data mart, and now you have a lot of raw data that you can query. But one of the interesting things about that pass-through is that along the way, you can analyze the data and take some automated actions. So you might be able to recognize some trends, some patterns, or some anomalies that require some immediate action. So you can take that action before an end user ever has to see it. And that helps with solving a lot of issues where responsiveness is key and that there is a narrow time window in which you need to respond for that event to create any value for you. And of course, as you have all this data stored in your data mart, in our case, the in-memory data store, there's a lot of opportunities for additional processing at a distributed level, meaning you can do a lot of the processing in parallel. And so as you have all this data that you can access very quickly and take action on very quickly, that helps to give a real-time advantage to any business that's running this. And finally, I want to point you to a few resources. On the left, at the Hazelcast blog site, we wrote a blog last year about a benchmark that our engineering team put through for 1 billion events per second with millisecond latency. And we did that in the cloud. And the interesting thing about this benchmark was that we were able to do it with very few servers. And I think that was the testament to the linear scalability of our software. So we have the performance, but we also run very efficiently. So you can perform 1 billion events per second on data in motion with a lot of different technologies, but the question is how much are you going to spend to be able to achieve that performance level? And we were able to do it very efficiently, and that becomes a very big economic advantage. And on the right, on blocksandfiles.com, there is a case study about Intesa Sanpaolo, Italy's largest bank, where they used Intel Optane and MemVerge and Hazelcast all together to essentially accelerate their business applications. So check out that story that was recently published. And that concludes my presentation. Thank you very much for watching.